Hello there, and welcome to the Whispering Science, where curiosity meets calm and the wonders of our universe gently ease you into a world of restful dreams. Picture yourself already tucked beneath the covers, your eyes heavy as twilight settles in. Now, I do hope this isn't too interesting that it keeps you awake. But if it does, well, at least you'll have learned something fascinating about exoplanets and the search for alien life. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. Knowing there are listeners across the globe, each with their own slumbering sky overhead, always warms my scientifically inclined heart. So settle in, get comfortable, and let's begin our quiet voyage into exoplanets, those mysterious worlds that orbit suns beyond our own. Imagine you're gazing up at a velvety night sky. Each pinprick of starlight could be the center of its own planetary system, a family of worlds spinning in orbits, like invisible dancers around a distant fire. For centuries, those specks of light were little more than hopeful puzzles, their mysteries shielded by impossible distance and the blinding brilliance of the stars they circle. As we drift into this subject tonight, think about what it means to gaze outward from our tiny blue planet into the vastness of the cosmos. Even our own solar system, with its 8 major planets, dozens of moons, and a scattering of smaller objects, stretches the imagination. But astronomers realized, as you may have guessed as you drift towards sleep, that our sun is just one among hundreds of billions in the Milky Way, and that each of those stars might have planets too. The universe, it turns out, may be awash with worlds, some familiar, some fantastical, and some holding secrets no dream could imagine. But how did we come to suspect this? And what does it mean for the age-old question, are we alone? That's the gentle mystery we'll sink into tonight. As we float through the universe together, let your thoughts meander from one distant sun to the next, pausing to ponder the possibilities that spin silently under their alien skies. Rest assured, no matter how far we wander tonight, we'll always return to the comfort of your own pillow and the steady certainty of our own planet Earth beneath you. Tonight, our sleepy stargazing will help you envision, calmly, slowly, what it truly means to live in a universe teeming with exoplanets, each one a world of wonder, huddled close to a star, twinkling quietly as you drift into dreamland. Since ancient times, humans have wondered if distant worlds might exist. Let your mind wander back in time, back beyond telescopes and rockets, beyond streetlights and electricity, to an era when the night sky was an untouched canvas above every village, hut, or wandering campfire. Early humans stared up at the stars, and even without knowing it, laid the foundation for the science of exoplanets, centuries before the word ever existed. You might imagine the ancient Greeks, such as the philosopher Epicurus, around 300 BCE, writing confidently that there are infinite worlds both like and unlike this world of ours. Greek and Roman thinkers speculated that the universe might be teeming with life, even if they couldn't know for sure what lay beyond the stars they saw. Across the ocean, in the classical civilizations of India, texts like the Vedas and later philosophical works sometimes hinted at multiple worlds circling in cosmic cycles, while ancient Chinese treatments of astronomy catalogued the motions of stars and planets, fueling dreams that the heavens themselves might be mirrored with Earth-like order. Indigenous peoples around the world created narratives linking the stars to earthly stories and cycles of life, sometimes describing the stars as campfires of ancestors or distant lands, lit far away from the world we know. These early stories were not yet science, but they show a strikingly familiar human trait, curiosity paired with imagination. Even as people learned to track the wanderers, Mercury, Venus, Mars, Jupiter, Saturn, across the night sky, the mystery of whether other stars also hosted their own planets lingered like a gentle whisper at the edge of night. In the Middle Ages and into the Renaissance, scholars began debating the structure of the cosmos with more precision. Some, like the philosopher Giordano Bruno in the 16th century, made a bold leap, He imagined an infinite universe filled with countless suns, each with its own inhabited worlds. For this and other heretical thoughts, Bruno paid dearly, but his vision echoes eerily in our modern discoveries. As telescopes appeared in the 1600s, scientists such as Galileo Galilei and Christian Huygens peered at Jupiter and saw its moons, immediate proof that there were worlds circling objects other than the sun. It was a profound moment, shifting human thinking. If Jupiter, a mere wandering star in the night, could have its own system, what about the thousands, millions, or billions of other stars shining faintly in the vast darkness? As centuries passed, science and storytelling intertwined. Novels, poems, and early science fiction. Think of H.G. Wells's The War of the Worlds, or Jules Verne's From the Earth to the Moon, invited readers to imagine traveling to distant planets, meeting alien creatures, or gazing down on Earth from afar. These were dreams, yes, but their roots dig deeply into the same soil as our more formal, methodical understanding of exoplanets today. You see, even as you settle in tonight, you're part of a much older story, one in which humans have always wondered, are there other worlds out there? Other places where life could emerge and look up at their own alien sky? That gentle curiosity, an ember glowing in the night, has fueled every scientific advance since, a soft, irresistible pull that still guides our telescopes skyward. The beauty of this curiosity is that it never truly fades. Today's scientists, with all their intricate instruments and sophisticated equations, share something essential with those early stargazers, a sense of connection to the untamed mysteries beyond. When you look at the sky, even half dreaming, your eyes heavy, you're not just seeing the past light from a billion years ago, but also participating in an ongoing human story. A dream, if you like, that every distant world is a question, waiting patiently for an answer. So as you slip deeper into relaxation, let your thoughts intermingle with those of the earliest dreamers. You can rest knowing that the wonder you feel is as old as our species itself, and that every story whispered under the stars is another stepping stone in our journey to understand the universe, and maybe, someday, to find that we are not alone after all. The search for exoplanets began in earnest with curious astronomers and their telescopes. For thousands of years, planets outside our own solar system remained just the stuff of speculation and stories. The technological and scientific hurdles were, quite simply, staggering. Other stars are so far away that their light arrives as a single, steady point, and any planet orbiting them is utterly lost in that brilliance. For all the certainty of philosophers or the fantastic visions of writers, the actual existence of exoplanets awaited the age of meticulous observation, patient instrumentation, and a slowly shifting worldview, one where evidence would become our guide. But the first true hints did not emerge until the 20th century, when advances in astronomy allowed scientists to scrutinize the sky with levels of detail never before possible. As you settle deeper beneath your blankets, imagine the generations of astronomers patiently guiding telescopes through the chilly night air, eyes pressed to the eyepiece, notebooks in hand, searching for changes so subtle that they might easily go unnoticed. For all their efforts, there was a persistent problem. The direct light of stars easily outshined any orbiting planets, making them invisible to the methods available at the time. Yet science grows through persistence and cleverness. In the early 1900s and well into the mid-century, as astrophysics matured, astronomers developed powerful new instruments, photometers and spectrographs, that could measure changes in starlight with incredible precision. Every twinkle and subtle shift was catalogued, and thoughts of planets around other stars remained tantalizingly out of direct reach. But scientists were getting closer, one incremental step at a time. Through the 1980s, a few puzzling observations stood out. For instance, small wobbles in the motion of certain stars were noticed, movements that couldn't be fully explained by binary star systems or random chance. Was it possible these motions were caused by the gentle gravitational tug of an unseen planet? Most astronomers were cautious, hesitant to claim a discovery so significant without ironclad evidence. As you might expect from the history of science, caution and skepticism held sway, with many fascinating results being declared inconclusive or uncertain. There was, simply put, a sense that direct discovery might always remain just beyond reach. Then came an extraordinary moment that would reshape astronomy and fire our quiet nighttime imaginations. In 1992, two radio astronomers, Alexander Vulshan and Dale Frail, made a discovery almost as strange as it was momentous. They found the first exoplanets not around a sun-like star, but orbiting a pulsar named PSR b 1257 plus 12, a dead, ultra-dense remnant star left over from a supernova explosion. By analyzing the timing of radio signals from the pulsar, they showed that tiny regular shifts were almost certainly due to three unknown companions tugging at the pulsar, a new family of worlds, more than 2,000 light-years away. Although these planets were hardly habitable, blasted by radiation and born in a catastrophic supernova, the cosmic principle was set. Planets existed outside our solar system, and we could detect them. A mere 3 years later, in 1995, came the first true glimpse of an exoplanet orbiting a sun-like star, 51 Pegasi b. Michel Mayor and Didier Queloz, Swiss astronomers working at the Observatoire de Haute-Provence in France, noticed a peculiar, regular wobble in the star 51 Pegasi. By measuring the Doppler shifts in the star's light, they revealed a planetary mass companion, a world about half the size of Jupiter, orbiting scorchingly close to its host. The detection was met with both amazement and skepticism, until repeated observations confirmed it and proved that exoplanet discovery was not just possible, but real. For this achievement, both scientists were honored with the 2019 Nobel Prize in Physics, recognition of a discovery as profound as any in the last century. Picture, if you will, the excitement of those nights. A handful of researchers anxiously recalculating their data, checking for errors, their hearts surely pounding with the knowledge that their lives' work had brought humanity to a turning point. Their telescopes, once just extensions of the human eye, had become portals to the realms imagined by storytellers and wondered over by philosophers. With each confirming observation, the veil lifted a little more. After these discoveries, a new era dawned. Telescopes across the world, and eventually orbiting high above the atmosphere, would turn their attention to the stars in a systematic hunt. Space-based missions would soon scan hundreds of thousands of stars for the subtle signatures of planets. Each detection was a triumph, a promise that the exceptional could become the expected. The great cosmic guesswork of our ancestors, the elegant theories of early scientists, and the first hesitant data points all came together. The search for exoplanets, long a dream, was now a science, carried forward by careful observation and continued curiosity. As you drift lower tonight, remember, these advances began with people just like you, staring up at the same great stretch of night, resolved not to let the mysteries of the universe slip away unanswered. Each discovery was a star in its own way, a point of light on the growing map of possibility, gently illuminating the path for us all as we journey together through this cosmic darkness. Let's discover the ingenious methods scientists use to spot faraway planets. In the quiet darkness, as you lie back and allow your thoughts to settle, imagine the extraordinary challenge facing astronomers. To detect a planet so faint and distant that it is utterly drowned in starlight, billions upon billions of times dimmer than the star it orbits. If trying to spot a firefly beside a searchlight from thousands of miles away seems impossible, you have some sense of the difficulty here. Yet human ingenuity has developed a remarkable toolkit, a set of methods, each clever in its own right, for finding exoplanets, even when we cannot see them directly. The first, and for a long while, the most fruitful technique, is the radial velocity method, sometimes called the wobble method. Here's the basic idea. Planets and stars actually orbit a common center of mass. When a planet tugs on its star as it circles, the star moves very slightly. Imagine a dance, where a heavyweight partner leads and a lighter one follows, but both feel the gravitational pull of the other. The result? The star gently wobbles in its position, moving toward and away from us across years or decades. This motion can be caught in the star's light itself, specifically through the Doppler effect, the same phenomenon that alters the pitch of a passing train's whistle, but here manifesting as faint shifts in starlight wavelengths. When the star moves toward us, its light is just a bit bluer. When it moves away, just a touch redder. By using ultra-precise spectrometers, such as the legendary HARPS instrument in Chile, scientists can measure changes in the velocity of a star as slight as 1 meter per second. This is about walking speed. Through this method, the earliest exoplanets, such as 51 Pegasi b, were brought out of hiding. But radial velocity is only the opening act. Another elegant detection method is the transit technique, which relies on the rare alignment when a planet passes directly between its star and our telescopes. When this transit occurs, the planet blocks a tiny fraction of the star's light, causing a brief, periodic dimming. If we monitor tens of thousands of stars carefully enough, recording their brightness night after night, a repeating, regular dip gives away the silent passage of a planet orbiting its parent star. This method requires, among other things, incredible patience and monitoring at a scale almost unimaginable before the age of digital detectors. The historic Kepler Space Telescope, which began its mission in 2009, observed over 150,000 stars, yielding thousands of exoplanet candidates through this technique. Each transit is like a fingerprint. How deep and how long the dip lasts tells us about the planet's size and orbit. These two techniques, radial velocity and transits, still account for the vast majority of exoplanet discoveries, but astronomers have more tools in their toolkit. Gravitational microlensing, for instance, takes advantage of the warping of space-time predicted by Einstein. If a star with a planet passes in front of a more distant star, its gravity acts like a lens, briefly magnifying the background star's light. If a planet is present, it causes a detectable, short-lived blip in this brightening. This method has even revealed exoplanets in regions of the galaxy otherwise beyond the reach of other techniques. Then there's direct imaging, which, while still extremely challenging, is improving every year. Special instruments called coronagraphs or star shades are used to block the overwhelming glare of starlight, allowing faint planets to be glimpsed beside their suns. Infrared telescopes, in space and on Earth, exploit the difference in heat emission between stars and planets to tease out the presence of giant Jupiter-like worlds. In recent years, this method has delivered actual photographs of exoplanets, glowing, blurry, but undeniably real, circling stars tens or hundreds of light years away. Timing variations provide yet another window into these hidden systems. In pulsar timing, regular pulses from a spinning neutron star, a pulsar, are monitored with exquisite precision. Any planet tugging on the pulsar will disturb these pulses. In transit timing variations, astronomers observe the minute changes in the regularity of planetary transits, hints that other unseen planets are exerting their own influence. Cutting-edge missions and telescopes, such as NASA's TESS and ESA's Cheops, now bring all these tools to bear, offering ever more refined views of solar systems light years from our own. New forms of analysis, machine learning and careful sifting of mountains of data help reveal the faint signs that would otherwise escape even the keenest observer. When you consider the sums involved, it's breathtaking. As of early 2024, well over 5,500 confirmed exoplanets have been discovered, most through these ingenious detection methods. Some are hot, some icy and lonely, some strange beyond imagination. But all were, for eons, simply specks lost in the light. Now we know many of their names and orbits, their sizes, and in some blessed cases, even hints of the gases swirling above their surfaces. As you ease deeper into relaxation, reflect on this. Our ability to seek out exoplanets, to find these secrets hidden among the stars, is one of the great quiet triumphs of human curiosity and tenacity. There is nothing hurried or reckless in this pursuit. Each discovery, patiently coaxed from the darkness, is a soft answer to an ancient longing, as if the night sky itself is gradually, gently, replying to the question we have always asked. Who else, or what else, shares this immense universe with us? A planet's faint shadow can whisper its presence across light years. As you let your breathing slow and your body relax, imagine an astronomer patiently watching a single star, its steady light flickering across a sensitive detector night after night. For most of human history, this light seemed constant, unchanging, unwavering, a touchstone of celestial predictability. Then, as our tools grew more precise and vigilant, scientists noticed a peculiar phenomenon. Every so often, a star's brightness dipped by the tiniest amount, just for a few hours or days before returning to normal. What could cause such a gentle, regular wink? The answer, as sleepily as a cloud drifting across the moon, is the silent transit of a planet, or sometimes more than one, crossing in front of its star. This phenomenon, called the transit method, is now the gold standard for detecting exoplanets. The mathematics behind it are surprisingly simple yet profound. When a planet passes or transits between its star and our telescopes, it blocks a fraction of the starlight, and that dimming can be measured with exquisite sensitivity. The dip is minute, often less than 1% of the star's total brightness for a Jupiter-sized planet, less than 0.1% for something more like Earth, but it is enough. The planet becomes, briefly, an astronomical puppet, casting a subtle shadow that tells us it is there. Imagine the delicacy required. Our Sun is over 100 times the diameter of Earth. Yet a planet as small as ours, passing in front of a similar star, can still produce a detectable dimming. For a distant observer looking at our solar system, the Earth's shadow would cause the Sun's light to dip by just 0.008%. Yet with high enough sensitivity, this is not only measurable, but repeatable, happening once every orbit, like a cosmic metronome marking the passing of years. Scientists look for this regular, precise schedule. If the dip recurs at stable intervals, we know a planet must be circling its star again and again. The method was first proposed in the late 20th century, but it was missions like NASA's Kepler Space Telescope, launched in 2009, that brought it to towering prominence. Kepler's mission was as ambitious as it was patient. The telescope would stare unblinkingly at a single patch of sky, monitoring more than 150,000 stars at once. Over its 9-year mission, it detected over 2,600 confirmed exoplanets and thousands more candidates, simply by recording the telltale shadows cast by planets as they transited their stars. The information we get from transits goes far beyond the mere existence of a planet. By measuring the depth of the dimming, scientists can estimate the planet's size. The deeper the dip, the larger the planet, at least in terms of its cross-sectional area. The interval between dips tells us the orbital period, which, combined with some clever geometry and knowledge of the star, allows us to estimate the distance between the planet and its sun. Longer periods mean wider orbits, echoing Kepler's own laws of planetary motion first articulated in the early 1600s, showing again how today's science builds directly atop the scaffolding of centuries-old discovery. But there's even more. If the telescope is sensitive enough, variations in the timing, depth, or even shape of each dip can hint at additional planets gravitationally tugging within the system, or in some cases, the presence of moons or rings. In a few marvelously rare cases, astronomers have watched as thin layers of a planet's atmosphere filter their star's light during transit. By spreading that filtered starlight into its constituent colors, a spectrum, they can actually identify particular atoms and molecules in the planet's gaseous envelope. With the transit method, we not only discover planets, but quite astonishingly, can sometimes begin to sniff their skies for the ingredients of life. This method does have its limitations, of course. Only a small fraction of planetary systems are oriented such that their planets actually cross in front of their stars from our line of sight. Think of flipping a coin. Most land on their edge, unseen. As a result, we necessarily miss many planets, seeing only the lucky few whose orbits are perfectly aligned for transits. Still, out of the hundreds of billions of stars in our galaxy, enormous surveys mean that even a tiny slice can reveal thousands of planets. And this is only the beginning. Recent space-based missions, like TESS, the Transiting Exoplanet Survey satellite, are scouring almost the entire sky, searching for transits around the nearest and brightest stars, perfect candidates for follow-ups with powerful observatories. Imagine, as you drift further towards sleep, the faint shadows of uncountable worlds flickering across their stars tonight, an ever-growing catalogue, each point of darkness a testament to the subtlety and patience of discovery. From the comfort of your bed, you share in the moment, a moment made possible by generations of wonder and years of quiet, methodical work, all aimed at finding the smallest of shadows sliding across the oldest of lights. Even the tiniest planet can make a star dance ever so slightly. As the night grows deeper and your body relaxes, let's gently explore another elegant technique used to discover exoplanets, the radial velocity method, sometimes endearingly called the wobble method. While the transit method seeks out shadows, the radial velocity method listens for the subtle music of motion, a star's tiny dance as it feels the gravitational tug of an unseen planetary companion. Imagine for a moment our own sun. Though we often think of the sun as the stable center, planets like Jupiter and even much smaller worlds exert a gravitational pull, causing the sun to sway ever so slightly in space. This mutual motion means that, in reality, both the star and its planet proceed around a shared center of mass. For most planetary systems, this center lies just inside the star's surface, so the star seems to wobble, a tiny rhythmic motion, forward and backward, drawn by the gravitational embrace of its orbiting worlds. The key to unraveling this motion lies in the exquisite sensitivity of modern spectrographs. Here's where physics offers its quiet magic. As a star moves toward us in its subtle dance, the waves of light it emits compress slightly, shifting toward the blue end of the spectrum. As it moves away, those waves stretch, shifting toward red. This effect, the Doppler shift, is familiar in daily life as well. A passing ambulance siren rises in pitch as it approaches and lowers as it moves away. For starlight, however, we detect this change not as a sound, but as a minute alteration in light's color. Now, just how subtle is this star's dance? For many exoplanets, the velocity changes are measured in meters per second, a brisk walk or a gentle bicycle ride. In 1995, it was this very wobble in the sun-like star 51 Pegasi that led Michel Mayor and Didier Queloz to the first confirmed detection of an exoplanet around a sun-like star. The star shifted back and forth by about 59 meters per second, just enough for sensitive instruments to measure. Worlds beyond the stars confirming their presence through a rhythmic, celestial ballet. Using the radial velocity method, astronomers have detected hundreds of exoplanets. The HARP spectrograph at the La Silla Observatory in Chile, for example, can measure star velocities with a precision better than 1 meter per second, akin to detecting a snail's pace from across a continent. These measurements are not isolated to massive planets alone. With persistent advances, scientists can now detect the impact of super-Earths, and even, in fortunate circumstances, planets only a few times more massive than our home. The method is not without its own set of challenges. Stars themselves can have cycles and natural jitter in their surfaces, oscillations, spots, and magnetic activity that can mimic the pull of a planet. The careful scientist must therefore gather data over many months, even years, seeking the regular beat that only an orbiting planet can provide. The length of the periodic wobble, called the orbital period, reveals the planet's year. The amplitude, or strength, of the wobble provides an estimate of its minimum mass. What's more, this subtle dance reveals only the motion along our line of sight. A planet orbiting face-on to our view eludes this method entirely. Still, for those orbits just tilted enough, the star's repeated tugs and releases, always in a fixed, predictable rhythm, add new entries to the growing catalogue of distant worlds. Amazing discoveries have emerged from these quiet measurements. Radial velocity has revealed planet types we never expected, such as hot Jupiters, enormous gas giants that orbit scorchingly close to their stars, circling them in just a few days. Traditional views of planetary system formation struggled to explain these unexpected systems, prompting scientists to rethink the processes that shape planetary neighborhoods throughout our galaxy and beyond. In rare cases, by combining transit and radial velocity data, astronomers can determine a planet's exact mass and radius, and thus its density. Density opens the door to further understanding, distinguishing rocky terrestrial worlds like Earth from gas giants like Neptune and Saturn, or water-rich worlds unlike anything in our solar system. Consider, as you nestle further beneath your blanket, the astonishing chain of inference required here. With just tiny shivers in starlight, we infer the presence of whole worlds. Think of how, in your own life, small signs, a subtle smile, a gentle rise in someone's voice, can reveal stories left unsaid. So too, the cosmos offers up its secrets through the faintest movements, planets that make their parent stars sway in the cosmic dark, dancing, always dancing, even when no eyes directly observe. As thousands of stars gently undulate under the pull of unseen company, our instruments stand vigilant, tuned to catch the next tiny dance. These cosmic wobbles write a soothing music, one note for each new discovery, the melody of a universe brimming with possibilities. Our technology is now catching faint, ghostly glimpses of alien worlds themselves. As you let yourself drift even more deeply into calm, close your eyes and try to picture the impossible. Seeing a planet, truly seeing it, with enough clarity to recognize its separation from the blinding light of its parent star. For most of human history, this was the stuff of dreams and stories, for the light from a star is millions or even billions of times brighter than that of any surrounding planet. Yet within the last 2 decades, technology and curiosity have slowly begun to tip the scales, setting the stage for something wondrous, the direct imaging of exoplanets. Direct imaging asks the astronomer to perform one of nature's great balancing acts. Imagine you're trying to spot a firefly, flitting right next to a stadium floodlight, and you have only the gentlest and most sensitive camera to capture the scene. The brilliance of the floodlight overwhelms everything, flooding your view and swallowing the faintest flickers. This is what astronomers face when they try to image a planet that's billions of times dimmer than its host star. Traditional telescopes simply weren't built for this challenge, but our ingenuity has yielded solutions both simple in concept and sophisticated in their execution. One of the most important tools in this quest is the coronagraph, a device that blocks out the direct light from a star, much like holding your thumb up to shield your eyes from the sun so you can see what's around it more clearly. Coronagraphs come in several forms, from carefully shaped masks in telescopes to sophisticated optical systems that use mirrors and lenses to cancel starlight with extraordinary precision. They allow the dim regions next to a star to be studied in detail, revealing the possibility of faint planetary companions shining faintly nearby. Another revolutionary approach is the starshade, which works not inside a telescope, but as a companion spacecraft. Picture a gigantic, precisely shaped disk, often tens of meters across, flying tens of thousands of kilometers ahead of a telescope in space. Its job is to block out the star's light before it ever enters the telescope, casting a shadow so that the telescope sees only the space around that star. The engineering for such a feat is breathtaking, requiring careful alignment across tens of thousands of kilometers, but it carries the promise of pushing direct imaging to whole new frontiers. Then there's the use of adaptive optics on ground-based telescopes, technology that measures the way Earth's atmosphere bends and distorts starlight, and then compensates in real time with nimble moving mirrors. The result is sharper, steadier images that can pick out exoplanets even from the surface of our turbulent planet. These systems are now so sensitive that they can spot massive gas giants orbiting sun-like stars mere tens or hundreds of light years away. What do we see when we finally glimpse these worlds? Rather than the crisp images you might expect from a breathtaking photograph of Jupiter or Saturn, direct imaging gives us glowing, slightly blurred dots, planets still, but swaddled in cosmic haze, showing up in the infrared spectrum rather than visible light. These are usually hot, young worlds, glowing with the heat left over from their formation, and orbiting far enough from their star to avoid getting lost in its glare. The very first direct image of an exoplanetary system came in 2004. Astronomers managed to photograph a massive gas giant around a brown dwarf known as 2M1207 in the constellation Hydra, about 170 light-years from Earth. Since then, a growing handful of worlds have joined the gallery, some orbiting in groups, with multiple planets circling together, each glowing dot a real place, tangible, and remote. Over the past decade, incredibly, entire planetary systems have been observed, such as HR 8799, where 4 planets, each several times the mass of Jupiter, swing around their young, bright star like pearls threaded on invisible strings. Visualization of these systems, created from a series of direct images collected over the years, shows the planets' changing position, confirming their orbits in real-time motion. Suddenly, what was once only the subject of calculation or inference becomes a star system we can see, its planets painted by photons caught after tens or hundreds of years of travel. With continued advances, especially as the next generation of telescopes, like the James Webb Space Telescope and future 30-meter ground-based observatories, come online, scientists hope to image smaller, cooler exoplanets, perhaps even super-Earths or worlds like our own, nestled quietly in alien habitable zones. The ultimate goal is not just to see these planets as points of light, but to dissect the faint precious rays reflecting off their surfaces or passing through their atmospheres, searching for chemical clues. Maybe, one day, even the colors of alien sunsets or the subtle blue of distant, liquid water. As you rest in the darkness, picture the power of this achievement. Humanity, patiently and quietly, coaxing real sights from the depths of space, no longer simply knowing other worlds exist, but beginning to see them as places, distinct and certain, their reality flickering gently at the edge of our vision. One by one, patiently, our technology is allowing us to greet these ghostly new worlds and, in doing so, expand the boundaries of what it means to explore from the comfort of our small planet. NASA's Kepler mission revealed just how common exoplanets might be as you nestle further into comfort, perhaps feeling the gentle weight of your blanket and the steady rhythm of your breath. Let's allow our minds to drift into one of the most transformative chapters in the history of astronomy. A story not of a single discovery, but of a flood, an awakening, a quiet revolution that changed our perception of the cosmos forever. This is the story of the Kepler Space Telescope. Launched in March of 2009, the Kepler mission was designed around a beautifully simple but profoundly powerful idea: to keep watch on a single modest patch of sky, no bigger than the size of your palm held at arm's length, and stare at it continuously for years, recording the brightness of over 150,000 stars. The telescope was placed in an Earth-trailing orbit, letting it avoid the flicker of our atmosphere, and equipped with detectors so finely tuned that they could spot light dips as slight as 20 parts per million. Kepler's quiet gaze wasn't meant to capture beautiful images, but to listen for the whisper of planetary shadows, using the transit method, patiently waiting for planets, both large and small, to cross in front of their stars. Over the course of its 9-year journey, Kepler became the night watchman of the galaxy. For the first time in history, we gathered a meaningful census, not just a list of oddities, but true statistics that could be applied to the whole Milky Way. And what Kepler found exceeded our wildest dreams. Instead of a universe with planets as rare jewels, we learned that planets are, in fact, everywhere. As of its final tally, Kepler discovered over 2,600 confirmed exoplanets and identified thousands more promising candidates. Some stars were found to have multiple planets, while others hosted planets in tight, dizzying orbits or precarious resonant dances. The power of Kepler's data lies in its comprehensiveness. It didn't just pick out the biggest or weirdest worlds. It detected planets across a dazzling range of sizes and orbital distances, from oven-hot gas giants skimming the surfaces of their stars, to rocky planets nestled in temperate, potentially life-friendly zones. Because Kepler focused on a pre-selected, statistically significant set of stars, its discoveries could be generalized, a first for planetary science. By the mid-2010s, astronomers could say with growing confidence that for every star in the Milky Way, there is at least one planet. The implication is breathtaking. With over 200 billion stars in our galaxy, there may be hundreds of billions of individual planets, and perhaps 40 billion Earth-sized planets orbiting in their stars' habitable zones. Kepler's discoveries began reshaping our understanding of what planetary systems look like. We learned that our solar system, with its neat arrangement and diverse range of planet sizes, might be an oddball. Many systems are packed with several planets in tight, close orbits, and super-Earths, planets larger than our own but smaller than Neptune, appear so often that their absence here in our home system is now a scientific mystery. Planets can huddle astonishingly close to their suns, enduring years that last only a few days, or circle together in intricate patterns of resonance and rhythm. Kepler's findings also seeded an explosion of discovery in related fields: stellar astrophysics, statistics, planetary formation theories. The mission taught us to look at the sky with new eyes, not as a scatter of solitary stars, but as a tapestry, with planetary systems woven tightly into the very fabric of the galaxy. Even the mission's challenges contributed. After a reaction wheel failure threatened to end operations, resourceful engineers repurposed the telescope for K2, a second act that scanned different regions, collecting a rich kaleidoscope of planetary discoveries across the ecliptic. Kepler's legacy lives on in every new mission launched to the stars. Its riches feed not only current studies, but will guide the next era of exploration. The Transiting Exoplanet Survey Satellite, TESS, the James Webb Space Telescope, and the European missions on the horizon all build on Kepler's foundation, targeting nearby stars for detailed study, searching for the faintest signs of life, and articulating a profoundly humbling truth. The universe is overflowing with planets, worlds upon worlds, spinning silently just beyond the reach of our naked eyes. So, as you relax and let go of the day's concerns, drift off with the knowledge that we don't gaze upward into a sky of emptiness. Quite the opposite. Behind every twinkle is the tantalizing possibility of entire systems, each with their own stories, maybe even their own nights and dreams. Kepler's gaze showed us we are part of a crowded, wandering galaxy, sharing existence with a breathtaking number of hidden neighbors, all waiting for us to notice their faint, distant light. Statistics now suggest that planets may outnumber stars. As you settle into an even deeper calm, perhaps feeling your mind begin to drift and dissolve the day, it's soothing to consider just how profoundly our view of the universe has changed, thanks to discoveries made in only the past generation. Where once we believed that stars, like our own sun, were rare hosts in a vast expanse of empty space, we now know that planets are not the exception, but the rule. Planets may be far more common than the very stars they circle. This is not merely poetic wonder, but a discovery rooted in solid, painstaking data. Astronomers, using missions like Kepler and the newer TESS, have sifted through their vast catalogues and performed careful statistical analysis. Each planet discovered, some found by the shadowy dance of transit, some seen through their star's gentle wobble, others even caught in ghostly photographs, adds a data point in this cosmic census. By accounting for observational bias, how many planets we might have missed because of their angle or distance. Scientists extrapolate from the thousands we've already detected to estimate the true population of the Milky Way. Current research suggests that, on average, there is at least one planet per star. More recent models, refined by advanced computer simulations and ground-based follow-up observations, hint that the true number could be far higher. Some studies propose there may be 2, 3, or even more planets orbiting, on average, around every star in our galaxy. Consider the scale. With 200 billion stars in the Milky Way, this would mean there are potentially 400 billion planets, or more, spinning in vast and intricate orbits throughout our cosmic neighborhood. Let that scale sink in for a moment. Picture a night sky full of stars, each one you see representing not just a single body burning in distant space, but with a family of planets swarming invisibly around them, some cold and lonely, others basking close to their parent sun, perhaps experiencing sunsets or storms that would boggle earthly imagination. These planetary systems are as diverse as they are numerous. We found hot Jupiters, gas giants orbiting so close to their stars that their years last only a few days, their skies ever bright with sunlight. We found tiny rocky worlds, many times denser than Earth, and mini Neptunes, intermediate-sized planets with thick gassy envelopes, occupying a size class that our solar system somehow missed entirely. But here's an even more remarkable realization. Some astronomers believe there may be as many as 1 trillion rogue planets. Planets that have been flung free from their home stars, wandering the galaxy alone, unlit except by distant starlight and the faint heat remaining from their birth. The notion that there are worlds adrift, silently moving through interstellar darkness, hints at a cosmos far richer and stranger than any ancient tale. Statistics also allow us to refine our search for life. By applying what we know of planet occurrence rates to different star types and zones of potential habitability, we can predict how many might be just right for the chemistry of life. For sun-like stars, the chances are nurturing. Roughly 1 in 5 may have a planet in the so-called habitable zone, where temperatures allow for liquid water to pool on the surface, one of the key requirements for life as we know it. Around red dwarf stars, which themselves greatly outnumber sun-like stars, the odds are even higher. Planets snuggle close to their dim, cool suns, with years that last just days or weeks, but with the right conditions, they could offer stable environments for eons. This shift from a sky of isolated stars to one overflowing with planetary families echoes in every branch of astronomy. It affects how we think about the origin of planets, the distribution of life, and even the fate of our own world. We now know that the story unfolding here, on this blue planet quietly spinning around an ordinary star, is part of a much larger, far grander narrative. Worlds are everywhere, not out there in some unreachable infinity, but as a fundamental routine output of cosmic processes. So as your mind gently descends into sleep, imagine the vastness filled not with empty blackness, but with the soft presence of billions of worlds, each turning with patient regularity, each a potential harbor of mystery, beauty, or even life. The universe, it seems, delights in company, offering us the chance to keep discovering new vistas, both in the tranquil darkness above and in the quiet moments between waking and dreaming. Not all alien planets are like Earth. Some defy our expectations in dazzling ways. As you let the last of today's thoughts dissolve and your mind opens gently to wonder, I'd like you to imagine walking through an endless gallery where each painting is an entirely new world. The farther astronomers have extended their search, the more they have learned that there is no typical or average kind of planet. Many of the first exoplanets we discovered surprised us, not simply by existing, but by being so unlike anything we had ever dreamed possible. Let's begin with the hot Jupiters, those gas giants that orbit astonishingly close to their parent stars. The inaugural detection of 51 Pegasi b, that historic exoplanet revealed in 1995, introduced us to a planet larger than Jupiter, but so close to its star that a year there lasts barely more than 4 days. This was not at all what planetary scientists expected. According to the models developed from our own solar system, gas giants should form far from their star, like our Jupiter or Saturn. Yet here were gigantic worlds, orbiting in tight, blistering loops, their skies perpetually bright, their clouds likely composed of vaporized metals and silicates. Temperatures on hot Jupiters can soar to thousands of degrees Celsius, with winds that would tear across the surface at thousands of kilometers per hour. Many systems feature super-Earths, planets with masses and sizes intermediate between Earth and Neptune. These worlds are missing from our own neighborhood, so their discovery quickly upended our theories on planetary formation. Some super-Earths are likely rocky, perhaps more massive cousins of our home, while others may be swaddled in thick, water-rich or hydrogen-rich atmospheres. The possibilities boggle the mind. Even stranger are the water worlds, planets whose composition may be dominated by water, with oceans hundreds, even thousands of kilometers deep, extending beneath mysterious high-pressure ices and perhaps a rocky core. No world in our solar system matches this category, yet evidence for their existence grows as we measure exoplanet sizes, masses, and densities more precisely. Imagine a world completely enveloped in ocean, with no continents at all, its surface hidden beneath perpetual clouds, its blue depths unexplored. Some exoplanets orbit 2 stars at once, reminiscent of the fictional Tatooine in Star Wars. These are known as circumbinary planets. Imagine the light of two suns rising and setting, their combined warmth complicating the planet's climate and sky. The Kepler mission uncovered several such systems, including Kepler 16b, which circles its two parent stars in a stately, unusual orbit. Even what constitutes a planet can stretch the imagination. There are puffy planets, gas giants even larger than Jupiter, but lighter in mass, their atmospheres so bloated that they would float if placed in a cosmic bathtub. In fact, the largest known exoplanet, WASP-17b, is nearly twice the diameter of Jupiter, yet has less than half its mass. Conversely, there are ultra-dense worlds like Kepler 10b, which packs almost 4.5 Earth masses into a radius only 1.4 times that of Earth, making it one of the densest planets known. There are also rogue planets, worlds that have drifted away from any parent star, traveling alone through the galaxy. These dark planets are nearly impossible to detect unless they pass in front of a more distant star and reveal themselves briefly through gravitational microlensing, warping the star's light by their very presence. Consider the atmospheric chemistry. We have detected planets where the clouds may rain glass, sideways, driven by supersonic winds, such as on HD 189733b. There are planets so scorching hot, such as Kelt 9b, that their atmospheres are being stripped away by their star's radiation. Some planets reflect almost no light, black as charcoal, while others, like Kepler 7b, are blindingly reflective, possibly due to high-altitude clouds made of molten silicates. Not to be outdone, there are also lava worlds, such as 55 Cancri E, where the dayside temperature is hot enough to melt rock, creating wild landscapes of magma oceans, and nightside eternally cold, all within a planet smaller than twice the size of Earth. The extremes challenge any earthbound imagination. All of these discoveries illuminate a truth that is both humbling and exhilarating. The universe does not lack for variety, and our Earth, while precious, is just one more node on a vast spectrum of planetary possibility. Each new world discovered brings its own lessons, hinting at unimagined climates, geologies, and possible chemistries, stretching the definition of what a planet can even be, and reminding us that the cosmos, with its endless creativity, always has further mysteries to offer. So as your mind floats into dreams, picture these strange and dazzling worlds, each with their own nights and days, their own storms, their own alien seasons, surprises waiting in every corner of the sky, teaching us that to expect the unexpected is one of science's greatest delights. Exploring the amazing variety of exoplanets helps us understand our own. Now, as your breath settles and your body finds its most comfortable position, let's meander quietly through the astonishing diversity of exoplanets that astronomers have catalogued. With each discovery, we gain perspective on what is unique and what is surprisingly ordinary about our own Earth. Just as traveling expands our view of home, so does exploring this exoplanetary zoo reveal the special and shared qualities of our solar system. We've already encountered some of the most dramatic planetary classes: hot Jupiters, icy giants, super-Earths, and mysterious mini-Neptunes. But what do these labels truly tell us? Our early solar system studies suggested that planets form in rather orderly fashion, rocky worlds close in, gas giants further out. Now, exoplanet surveys show us systems very different from ours, with giant worlds hugging their stars, small rocky planets packed tightly together, and everything in between. For instance, super-Earths, planets larger than Earth but smaller than Neptune, turn out to be among the most common types of planet discovered. It is humbling to realize our solar system's apparent lack of super-Earths is in fact an exception in our galactic neighborhood. Let's delve a little into how astronomers categorize planets based on what they measure. The first factors are a planet's size, mass, and orbital period. From these, scientists construct a rough picture of a world's composition. Less massive, small planets tend to be rocky like Mercury, Venus, Earth, and Mars. Those between 2 and 10 times Earth's mass could be rocky, water-rich, or cloaked in thick hydrogen and helium atmospheres. Gas giants, on the other hand, overwhelmingly consist of hydrogen and helium, sometimes with cores made of heavier elements. The radius gap is a term that arises from studies of exoplanets. When plotting exoplanets by size, scientists noticed a curious scarcity of planets with a radius about 1.5 to 2 times that of Earth. This division likely reflects important details about how planets develop and hold onto their atmospheres, a clue to both the formation of our Earth and the surface conditions on distant worlds. Temperature, too, varies across a dramatic range. Thanks to the immense capabilities of the Kepler mission and more recent surveys, we've found extremely hot planets where temperatures soar thousands of degrees and chemical reactions happen that we'd never find on Earth. Others orbit faint, cool red dwarf stars and could be tidally locked, presenting one face forever to their sun, resulting in dramatic climatic divisions between a sunlit side and a perpetual night side. Some planetary systems teased out of distant starlight are so closely packed that if you stood on one planet and looked up, you might see several other neighboring worlds larger than the Moon appears in our sky. Tantalizing hints of gentle orbital ballets unseen here. Others lie staggeringly far from their star, perhaps orbiting in lonely, slow ellipses that would make a single year last centuries. The diversity deepens when we consider planetary atmospheres. Using spectra from transiting planets, astronomers have found atmospheres filled with water vapor, sodium, and even titanium oxide. Some hint at clouds of silicates, some at thick layers of methane. The chemistry of a planet's atmosphere shapes its color, temperature, and even the weather. Think of Jupiter's swirling storms or Venus's perpetual overcast extended, on exoplanets, to even more bizarre extremes. Why does all of this matter to us? First, it's a vivid reminder of how planetary processes work on a cosmic scale. Studying exoplanets allows us to test our models of planet formation, migration, and stability. For every rule written from our own solar system, there's now at least one distant world that seems to break it. The discoveries refine our theories, pushing us to a fuller understanding of how universal, how repeatable the recipe for planets might be. Second, this variety sharpens the uniqueness and fragility of conditions that support life as we know it. Seeing the incredible range of planetary temperatures, compositions, and climates, we better appreciate the intricate balance that allows Earth to be habitable. Details like plate tectonics, a stable magnetic field, a temperate climate, and abundant water all seem, from a cosmic perspective, like rare gifts, factors that elsewhere may combine in very different ways to create strange and even more wonderful worlds. Finally, by studying these exoplanetary cousins, we prepare ourselves for the day when we might truly detect another Earth, a rocky planet with an atmosphere rich in water vapor and oxygen, sitting just the right distance from a quiet star. Every new exoplanet found is a stepping stone, narrowing down where we should focus our search, teaching us not only what is possible, but what is probable. So as you drift, meditating on distant orbits, remember, learning about other worlds allows us to value our own. We are not alone in the universe, at least not in the structure of planets. And that cosmic kinship makes the Earth beneath you, with its familiar gravity, breathable air, and sparkling oceans, feel more precious and beautiful than ever. Not too hot, not too cold, but just right for life as we know it. There's a gentle story astronomers tell, echoing the old fable of Goldilocks, about the habitable zone. Tonight, as you settle into comfort, imagine us curling up to listen to this scientific version of finding a porridge that is not overheated nor cold, but just right, a sweet spot where a planet could host liquid water and perhaps a kind of life we might recognize. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where conditions might be right for liquid water to exist on a planet's surface. If a planet circles too close, oceans would boil away, leaving deserts or even a scorched surface stripped bare by stellar radiation, what we see on Venus, but even more extreme. Too far, and any water would freeze solid, blanketing the world in permanent frost and ice, a cosmic winter such as we find on Mars or the moons of the outer solar system. But within that narrow band, neither too hot nor too cold, there's hope for gentle surface temperatures, where rivers might flow and clouds might drift above living seas. Where this zone sits depends on the star. Our own Sun, a fairly middle-aged star, sets its habitable zone roughly where Earth, and in a broader sense, Venus and Mars orbit. For hotter, brighter stars, the zone lies farther out. For cool, dim stars called red dwarfs, the habitable zone huddles much closer in, often within orbits smaller than Mercury's in our solar system. The breadth of a habitable zone varies, and the zone itself changes slowly over a star's lifetime, moving outward as the star grows warmer with age. Finding planets in this zone is the source of much excitement for astronomers. Kepler's treasure trove yielded dozens of rocky worlds in or near their star's habitable zones, with some, like Kepler 186f, capturing the public's imagination as the first potentially Earth-sized exoplanet circling in that just right region around another sun. Later missions like TESS are adding to this list, seeking especially those that orbit bright nearby stars, where follow-up studies are possible. But the story is more nuanced than mere distance. For a planet to truly be hospitable, many other factors must align gracefully. The planet needs a stable orbit, avoiding wild swings in temperature. It needs the right mass to hold onto an atmosphere, yet not so massive as to turn into a gas giant. It's ideal to have some form of greenhouse gases, perhaps carbon dioxide or water vapor, to gently warm the surface, as Earth's atmosphere does. Plate tectonics can help cycle nutrients and stabilize climate over eons, and a magnetic field shields from harmful cosmic rays. We know many of these ingredients only because our Earth provides such a careful laboratory, teaching us that just right is actually a delicate interplay of variables. There's also the matter of time. A planet might be habitable early in its life, but lose that potential as its star ages and grows brighter. Conversely, a world now icy or hot may not always have been that way, a reality underscored by Mars, which shows evidence of ancient lakes and rivers, and Venus, which might once have been wetter, more temperate, and almost perhaps Earth-like. In our search so far, we've found worlds that fill the habitable zone across every kind of star. Red dwarfs, smaller and cooler than our Sun, vastly outnumber Sun-like stars in the Milky Way, and may host billions of worlds in tight, fast orbits, receiving warmth enough to melt ice, yet close enough that stars can sometimes bathe them in flares or radiation. Some models suggest that these close-in worlds could become tidally locked, always showing one face to their sun. Permanent day on one side, eternal night on the other, each with their own extremes, and perhaps only a narrow band of twilight where conditions might suit life. The boundaries of the habitable zone are, in fact, always shifting, narrowed or widened by a planet's atmosphere, its geologic and volcanic activity, or even the presence of life itself. Earth and its sibling worlds taught us that habitability is a spectrum, not a single number. Life may emerge in niches of a larger range we haven't yet imagined. What's so comforting, though, is this. The Goldilocks zone seems to repeat across the galaxy, spread generously among various types of stars, and this cosmic generosity means that there could be billions of potential homes for life. Every new world found in that gentle, temperate zone is another pinprick of possibility, a place where maybe, just maybe, the miracle that happened here has echoed somewhere else. As you drift towards sleep, imagine each planet nestled in its star's embrace, some circling red embers, others golden suns, a little closer, a little farther. But for a fortunate few, resting in that tranquil, life-permitting space where liquid water and perhaps curiosity itself can thrive. By sniffing atmospheres, scientists hope to spot signs of life. As you slip further into comfort, it's remarkable and a little magical to consider how modern astronomers are not content to merely count the planets out there. They long to meet them, to find out what fills their skies, and to look for subtle hints that might reveal the presence of life. This pursuit leads to a quietly astonishing scientific art, reading the atmospheres of exoplanets from afar, sampling their invisible breath using nothing more than the light of distant suns. Let's rest a moment on this gently complex process. When a planet crosses in front of its star, as in the transit method, a sliver of starlight skims through the planet's atmosphere before reaching our telescopes. Molecules and atoms within the atmosphere block specific wavelengths of this light, imprinting dark lines, almost like a barcode, onto the star's spectrum. Astronomers call this process transmission spectroscopy. By carefully dissecting the colors and lines in the stellar light before, during, and after a transit, they extract a fingerprint of the planet's atmospheric makeup. The technique is as delicate as it is powerful. The difference in starlight caused by a passing atmosphere can be less than 1 part in 10,000, demanding extreme precision and patient observation. Yet from these faint alterations, scientists have uncovered water vapor, methane, sodium, potassium, carbon dioxide, and even the beginnings of more complex chemical patterns, even from worlds hundreds of light years away. Telescopes tuned for such work, like the Hubble Space Telescope, and more recently, the James Webb Space Telescope, JWST, have revolutionized our understanding of exoplanet atmospheres. Hubble, for instance, first detected sodium in the atmosphere of HD 209458b in 2001, a proof that we could, indeed, sniff the skies of alien worlds. JWST, operating primarily in the infrared, now provides an even richer palette, teasing out thermal structures and the chemistry of smaller, potentially more Earth-like planets. Different molecules absorb light in different places along the spectrum. Water vapor absorbs well in the infrared, while sodium and potassium imprint distinctive features in visible light. Detecting these signatures can tell scientists if a planet has thick clouds, clear skies, haze, or a surface deep beneath a blanket of gas. With good fortune and many repeated observations, planets with high, thin clouds can be differentiated from those with dense, choking atmospheres, or those covered by glittering oceans or dust. Why is this so crucial for life? On Earth, life continually modifies the composition of our atmosphere, especially gases like oxygen and methane. If these are found together elsewhere, it may hint at living processes at work. When we sniff another world's air and notice oxygen in combination with methane or other disequilibrium gases, molecules that react and remove each other unless something like biology is replenishing them, we suspect something interesting may be happening on the ground. This is not just theoretical. Over the past decade, discoveries have included planets with water vapor-rich atmospheres, lava worlds wrapped in vaporized minerals, and possible signs of photochemical smogs, layers created by ultraviolet starlight interacting with molecules in the air. We can even infer the presence of clouds, winds, and day-night temperature differences, mapping the planet's weather in broad, subtle strokes. Future telescopes, such as the Nancy Grace Roman Space Telescope, and even more ambitious hypothetical observatories, may find ways to tease out faint emissions of oxygen or the spectral signs of complex organic molecules around truly Earth-like planets. Spacecraft like JWST are already targeting the habitable zones of nearby red dwarfs, subscribing to the hope that if life is even a little bit common, its chemical signature may drift across interstellar space to our watchful eyes. It's a search that proceeds serenely, step by step. No one spectrum gives a clear answer, just as no single breeze tells you everything about the weather outside. But with accumulation, comparison, and careful modeling, we are learning to recognize the planetary weather patterns of alien skies. In these subtle, otherworldly signals, scientists hope to find hints, the twinned breath of a living world, some precious blend of gases that can only be maintained by something astonishing down below. So, as your mind floats between wakefulness and sleep, imagine a web of faint connections, our telescopes inhaling, ever so gently, the light of distant sunsets, looking for a telltale signature, perhaps the faintest cosmic hello, whispered by alien life forms across the vast, embracing dark. Identifying possible fingerprints of living things on distant planets. As you settle beneath your blanket and let the room grow quieter, let's gently unwind one of the most intriguing and elusive questions in all of astronomy. If we can taste the atmosphere of a distant world, what exactly would count as proof, or even a hint, that life might be thriving there? This puzzle leads us to the concept of biosignatures, those special chemical fingerprints, combinations, or patterns that might only be produced or maintained by living organisms. Let's start here at home. On Earth, our planet's air is shaped by life in subtle but measurable ways. About 1/5 of our atmosphere is oxygen, a gas produced almost entirely by plants and cyanobacteria during photosynthesis. Left to chemistry alone, oxygen would quickly react with rocks or organic matter, and disappear. It is replenished constantly by living things. Likewise, methane, another key biosignature gas, is made by bacteria in wetlands, cows, and other life forms. On an oxygen-rich planet, it would swiftly break down unless something kept creating more. The simultaneous presence of both oxygen and methane, in the right amounts, is difficult to explain through non-biological processes, especially over long stretches of time. This dynamic duo forms the classic example of a biosignature, a combination of chemicals whose ongoing coexistence is a clue that life might be at work. When astronomers search for such fingerprints in exoplanet atmospheres, they hope to find gases like these standing out in the planetary spectra, perhaps water vapor at the right temperatures, coupled with oxygen, ozone, methane, or even carbon dioxide. Some scientists suggest we go further, exploring other combinations too: nitrous oxide, sulfur compounds, or more exotic molecules, which could point to unusual metabolic pathways, perhaps the breath of a truly alien biology. But atmospheric gases are not the only biosignatures. Some possibilities involve seasons or rhythms. On Earth, spring and summer bring a bloom of plant life reflected in the red edge of our planet's spectrum, a sharp change in how much light is reflected at specific wavelengths, thanks to chlorophyll in leaves. If we observed a distant world whose reflected light changed with its seasons, or displayed a similar red edge, it might hint at photosynthetic life spreading or withdrawing over continents and oceans. Another branch of biosignature science looks for pigments, colored substances produced by organisms for photosynthesis, protection, or display. Even strange colors, like the purple hue produced by certain salt-loving microbes on Earth, could, if detected, serve as tantalizing signs. Currently, these pigment biosignatures remain more theoretical, since present instruments aren't quite sensitive enough. But as technology advances, they offer fresh targets for future investigation. Yet, biosignatures must always be interpreted with careful skepticism. Astronomers are wary of false positives. There are natural, geological, or even photochemical processes that can mimic biosignature gases, especially around stars different from our Sun. For example, ultraviolet light from active red dwarfs may split water vapor and create oxygen or ozone without a single living cell. Volcanic activity, lightning, or the interaction of sunlight with certain minerals can all generate gases we once thought unique to life. That's why scientists speak in terms of biosignature patterns or contradictory chemistry, looking for combinations or behaviors that are very difficult to explain except by the ongoing work of living things. There's also the matter of context, the type of star, the planet's surface and temperature, its potential weather and climate cycles. All must be factored into any claim of a biosignature. A true discovery would come not from a single measure, but from an intricate web of evidence, an atmosphere out of equilibrium, chemicals in surprising balance, rhythms that match seasons, or perhaps one distant day, something that looks suspiciously like city lights on the night side of a planet. With every telescope and mission, from the JWST to the coming generations like the Extremely Large Telescope and specialized space missions, we move one small step closer. Each spectrum, each atmospheric sample, piles up a little more evidence, narrowing the search and refining our questions. Ultimately, the hope is to find a world where the chemistry makes no sense, unless, somewhere on that surface, life is hard at work, breathing, eating, transforming the sky in a way that only living things can. So, as you let yourself drift towards sleep, imagine those subtle, impossible fingerprints building up on some faraway exoplanet, each one a quiet invitation to wonder. Perhaps, in the dreams that await, you'll wander across an alien meadow or watch new sunlight glint off unfamiliar leaves, exploring from the comfort of your room the possibility that we are, after all, not quite alone, considering why, with so many worlds, we haven't heard from anyone yet. Here, in the deep quiet of night, you might find a sliver of curiosity flickering gently. If there are so many planets and perhaps so many places that could harbor life, why has our search for other beings, other minds looking out into the universe, so far returned only silence? This is the gentle riddle known as the Fermi Paradox, named after the famed physicist Enrico Fermi. Fermi first voiced this puzzle in 1950, at lunch with other scientists in Los Alamos, New Mexico. The question was both simple and stunning. Where is everybody? If our galaxy alone contains billions of sun-like stars, many with planets in their Goldilocks zones, and if the universe is so old, giving plenty of time for life to arise, persist, and spread, why don't we see unmistakable signs of life, intelligence, or engineering out there? The paradox becomes even starker when you start to do the math. In 1961, astronomer Frank Drake devised the now famous Drake equation, a way to estimate the number of civilizations in our galaxy capable of communicating with us. Each term of the equation reflects a cosmic ingredient: the rate of star formation, the fraction of stars with planets, the number of habitable zone planets per system, the likelihood of life developing, the probability of intelligence emerging, and the average lifespan of a communicative civilization. Even with modest assumptions and the benefit of our recent exoplanet discoveries, the numbers can quickly suggest there should be many civilizations out there. Yet all our telescopes and receivers, all our scientific listening, remains met with cosmic quiet. So what could be the explanations for this great silence? As you let these questions gently spiral in your mind, you'll find the answers are both sobering and wondrous. Some scientists propose that life itself, going from chemistry to biology, is far more difficult than we imagine, and that even with billions of worlds, few actually witness the transformation from unfeeling matter to thriving cell. Others wonder if life might in fact be quite common, but the rise of intelligence, especially technology capable of sending signals into space, is much rarer, an evolutionary leap that only happens in the rarest cosmic gardens. It's also possible that alien civilizations are out there, but their lifespans are short. Technological societies could bloom and fade in the blink of astronomical time, missing one another in the vast stretch of cosmic history. Or perhaps they exist, but have no desire or ability to communicate. They may use forms of communication beyond our technology, choose to remain quiet, or simply focus inward, unaware of or uninterested in communicating with new cosmic neighbors. Then there is the tyranny of distance and time. Even at the speed of light, signals take years to leap between stars. Civilizations may simply be too far apart, their signals dimming before reaching us, or swept away by the turbulent storms of interstellar dust. There is also the zoo hypothesis, the idea that we are being deliberately avoided or watched, our planet left undisturbed until we are deemed ready for contact. A more optimistic possibility is that the indicators we seek, radio signals, technosignatures, city lights, or gigantic structures, are either fleeting or subtle, present but missed amid the glare and noise of the cosmos. We may only now be reaching the threshold of technology where such signs could be seen. There's something quietly profound and comforting in the Fermi Paradox. It highlights how much more we have to learn about life, evolution, and the cosmos itself. Science has transformed the question from "is there life out there?" to "why haven't we found it yet?" And are we even seeking in the right way? This is not a puzzle to keep you awake, but an open invitation to curiosity, a reminder that not knowing is itself a beautiful stage in every great exploration. As you edge closer to sleep, imagine the galaxy as it truly is, ancient, immense, and still mysterious, filled with worlds and the possibility of others sharing the same wonder that you feel right now. The silence we experience may be temporary, a prelude to future discoveries, or perhaps a gentle cosmic solitude uniquely ours, for now. Let these questions wrap you like a soft blanket in the comfort that comes from joining the greatest search of all, searching not just for others, but for our place in this vast, star-filled night. Gently listening for cosmic signals, scientists hope for a whisper from the stars. Now, as your breathing becomes slower and even more tranquil, let's drift further into the quiet side of the search. The patient, night-long listening for signs of life, the work of SETI, the search for extraterrestrial intelligence. SETI represents both an organization and a concept. The hope that among the countless star systems crowding our galaxy, somewhere there exists a civilization curious enough and capable enough to send messages or even accidental signals out into the universe. Imagine rows of radio dishes like great metal ears perched on mountaintops or desert plains. Over the past decades, scientists have used instruments such as the iconic Arecibo Observatory in Puerto Rico until its collapse in 2020, and today, facilities like the Allen Telescope Array in California. These arrays of telescopes point themselves toward promising stars, collecting faint radio waves, artificial or natural, that have traveled light years across emptiness. SETI researchers sift through torrents of data, searching for signals that stand out from the cosmic noise. Something narrow and regular, a pattern too precise and sustained to be caused by known celestial phenomena. The idea is charmingly straightforward. Humans have been inadvertently sending radio and television signals into space for about a century. If another civilization is out there, and if they are tapping into similar technologies, even just by accident, their broadcasts could reveal their existence. The hope is to catch a beacon, perhaps a purposeful repetition or sequence, an encoded greeting, or even an incomprehensible but obviously artificial signal. In a few famous moments, SETI efforts have glimpsed intriguing possibilities, such as the WOW signal of 1977, a strong, unexplained burst near a frequency favored by astronomers as a channel for interstellar communication. Yet to this day, no signal has been repeated or confirmed as an unambiguous message from another intelligence. SETI isn't limited to radio waves. Recent searches include optical SETI, which scans for short, powerful flashes of laser light, and even more ambitious hunts for technosignatures. These are signs of advanced technology, perhaps gigantic orbiting structures, pollution in exoplanet atmospheres, or even the subtle night-side glimmers of city lights. Instruments like the James Webb Space Telescope, alongside the largest and most sophisticated radio telescopes on Earth, are now allowing us to look for these technosignatures in the atmospheres of distant planets, or through changes in starlight. There's a peaceful, contemplative quality to this search. Night after night, year after year, astronomers listen. The data streams in, mostly static, mostly the natural hums and pings of pulsars, the bursts of cosmic dust, the random chatter of the universe itself. But SETI teaches the power of patience and openness. All it might take is one clear signal, one unmistakable pattern, to remind us that across the great darkness we are not alone. In the meantime, these silent nights spent listening, tuning, analyzing, and sifting become a kind of shared cosmic meditation. Amateurs and professionals alike can take part. Anyone, anywhere, can download chunks of SETI data and help search for unusual patterns. It's a global effort conducted from the comfort of Earth's rolling hills, city rooftops, and university labs, each one turned with hope towards some likely star. If, as you settle deeper, you find yourself wondering what we'd do if we detected such a signal, know that scientists, philosophers, and even international committees have mused over these questions. Communicating with another intelligence would require caution, humility, and cooperation. How would we encode a response? What would we say to beings who may not share our biology, culture, or history, but would share at least the wonder of knowing the night? So, as your mind eases near the edge of sleep, picture the great network of telescopes around the world, their dishes slowly sweeping the heavens, each one quietly hoping for a simple hello or the faintest cosmic signature. It's a comfort to realize that humanity does not listen alone. We listen together, guided by curiosity and awe, attuned to the distant, patient music of the stars, imagining the forms life could take far beyond Earth's familiar boundaries. As tranquility deepens around you, let's wander, very gently, into the delightful and mind-stretching possibilities of alien life, a realm not of little green men, but of biology shaped by environments as diverse and unpredictable as the exoplanets we've now discovered. Our understanding of life is rooted naturally in what thrives here on Earth. Yet as science explores planets that are hotter, colder, darker, or more exotic than anything in our solar system, astrobiologists open their minds to forms of life that are truly beyond the familiar. On Earth, life shows extraordinary adaptability. Some organisms survive in boiling hydrothermal vents deep under the ocean, living without sunlight, dependent on the chemistry of Earth's crust. Others persist in the driest deserts, in high radiation zones, or in waters so acidic or alkaline they would dissolve almost anything else. These so-called extremophiles provide a roadmap for the search elsewhere. If life can thrive in Earth's most severe environments, might it not evolve in places that to us seem hostile or even impossible? Let's imagine some of these alien environments. Picture a planet tightly locked in orbit around a dim red dwarf, one side frozen in perpetual night, the other basking in endless though faint daylight. On such worlds, life, if it exists, might cluster in a twilight ring, a never-ending dusk where temperatures are steady and water may remain liquid. Here, plants, if there are any, might use pigments suited to capturing the feeble reddish glow of their sun, creating landscapes shaded not in green, but in deep reds, purples, or even black, optimized for a different kind of photosynthesis. What if the world is an ocean planet with seas hundreds of kilometers deep? Life there may never touch a solid bottom. It could float, swim, or form vast colonies in sunlit upper layers. Think of plankton or jellyfish analogues, evolving unique survival strategies, perhaps using minerals from the water to form floating air sacs, or collect light with biochemistry unfamiliar to us, forming drifting meadows of alien seaweed. The deeper you go, the higher the pressure. Organisms here could use unique adaptations, such as silica or metal-laced proteins, to resist crushing forces. Even stranger, on planets with thick cloud-laden atmospheres, life may be airborne. Scientists have speculated about floaters, creatures that ride planetary winds, perhaps absorbing chemical nutrients in swirling, storm-ridden skies. On a gas giant, you might find life evolving in thick atmospheric layers with just the right combination of temperature and chemistry, not unlike speculations about possible life high in the clouds of Venus. Then there are icy worlds, perhaps orbiting far from their star, blanketed in miles of frozen crust, but warmed underneath by tidal forces or radioactive decay. Just as Europa and Enceladus in our solar system may hold subsurface oceans, exoplanets could hide life deep within, fishing energy from hydrothermal vents, living without any need for sunlight at all. Life's chemistry, too, need not always be as we know it. While water is our planet's universal solvent and carbon its backbone, astrobiologists ponder alternative possibilities. Could ammonia, methane, or even supercritical carbon dioxide lakes serve as effective agents for molecular assembly? Could silicon, sulfur, or phosphorus play a much greater role in alien metabolisms, supporting biologies suited to extremes of heat, cold, or acidity? These are not just the stuff of fiction, but real scientific inquiries born from our growing understanding of chemistry and the constraints, yet potential flexibilities, of life. The imagination extends to life scale as well. What if the dominant life forms are microbial, never assembling into complex multicellular organisms like plants or animals? Or could intelligence take forms utterly foreign to our own, such as distributed collective consciousnesses? Creatures more like vast mats, networks, or biochemical computers than single entities. None of these might-be's are idle fantasies. They are reasonable steps from the variety of planetary environments revealed by exoplanet discoveries and from the inventiveness of biology right here on Earth. Every new extremophile found, every newly mapped alien atmosphere, every calculated range of planetary temperatures broadens the boundaries of where and how life could arise. As you approach sleep, allow these possibilities to gently unfold in your thoughts, a cosmos not limited to Earth's greens, blues, and browns, but one sparkling with exotic, diverse, perhaps profound forms of life. Perhaps, among the myriad worlds spinning in quiet darkness, there are living things, plant, animal, microbial, or something unimagined, tracing out their own complex stories, dreaming their own dreams under unfamiliar stars. Looking outward helps us appreciate Earth's unique place in the cosmos. As your room grows quieter and your eyelids grow heavier, let's gently reflect on a truth that every planet hunter, every stargazer, and every curious mind eventually encounters. The more we study other worlds, the more we see, sometimes in unexpected detail, just how precious and extraordinary our own planet truly is. The search for exoplanets, for alien life, or simply for a cosmic perspective, is as much about understanding ourselves as it is about finding company in the universe. Each new exoplanet discovery gives us a comparison, a way to sharpen the profile of Earth against the limitless variety of the cosmos. With every data point, planets roasting under twin suns or buried beneath ice, worlds wrapped in poisonous gases or scorched to cinder in infernal heat, we realize that Earth's delicate balance is, in a cosmic sense, remarkable. There's nothing inevitable about our world's gentle climate, breathable air, oceans that endure, or the calm, shining stability of our yellow sun. Consider, for instance, the size and position of our home. Our sun is a fairly standard G-type star, long-lived, stable, neither too hot nor too dim, and Earth's orbit sits within the habitable zone, at the right distance, not only for liquid water, but for an enduring dance of evaporation and rainfall. Our atmosphere is thick enough for warmth and thin enough for light. It holds in just enough greenhouse gases to stave off freezing, yet is not so heavy as to turn the surface into a blazing furnace, as happened to Venus. Think, too, of Earth's geological and magnetic uniqueness. Our planet's internal dynamo generates a magnetic field that shields us from cosmic rays and solar storms, preserving not just technology and infrastructure, but life itself. Plate tectonics help regulate the climate over eons, cycling carbon and renewing soils. The Moon, with its stabilizing influence, prevents wild swings in Earth's tilt, keeping our seasons moderate and regular. Most exoplanets, even those that appear in a habitable zone, may lack these stabilizers. They might tumble erratically or experience catastrophic freezes and thaws that prevent the evolution of complex life. Our biosphere is the greatest marvel of all. Across billions of years, life here has shaped and been shaped by the planet's atmosphere, cycling carbon, oxygen, and nitrogen in a balance so subtle and persistent, it nearly seems miraculous. And as exoplanet science grows, including the search for biosignatures and the modeling of worlds both more hostile and more inviting than Earth, our appreciation for this collaboration between planet and life deepens considerably. The lessons run deeper still. Looking out into the universe, we see that while planetary systems are common, arrangements as orderly as ours are comparatively rare. Many exoplanet systems show large super-Earths close to their stars, or tumultuous, tightly packed orbits where gravitational tugs cause chaos that precludes long-term stability. Giant impacts, a fate that befell Earth in its tumultuous early days but ultimately resulted in our Moon, can destroy or radically reshape young worlds. Even so, the fact that we exist, that life found a foothold on this small blue orb and evolved to consciousness, is a testament to a long, unbroken chain of fortunate circumstances. This cosmic perspective does not make Earth insignificant, far from it. It makes our home more valuable, more fragile, and more deeply beautiful, for it is the product of a universe of chance, chemistry, and constant change. We come to see that the waters we drink, the air we breathe, and the familiar constellations overhead are not guaranteed, but are the fruits of rarity and resilience. So, as you rest, let your mind embrace both the vastness of the universe and the intimacy of planet Earth. We are, in a very real sense, cosmic citizens, our bodies made of atoms forged in ancient stars, our thoughts the flowering of billions of years of planetary labor. Let that knowledge be a comfort, that in searching the stars, we better understand our own beginnings, our place, and our duty to care for this world, a world at once familiar and, in all the universe, perhaps unmatched. Exciting telescopes on the horizon will soon open even wider eyes on alien skies. As the night grows quieter and your mind teeters on the edge of dreams, it's comforting to know that the search for exoplanets and alien life is not a story with a single ending. It is a journey, growing richer with each generation, each new leap in our ability to sense and understand the cosmos. Even now, astronomers are preparing and building new tools, telescopes that will transform our ability to glimpse the skies of distant worlds in unprecedented detail, bringing the shadowy hints and distant points of light into sharper, more revealing focus. Perhaps the most eagerly anticipated newcomer is the James Webb Space Telescope, JWST, which became operational in 2022. JWST is not merely a successor to the Hubble Space Telescope. It is a leap into the realm of the infrared, allowing us to peer into the cool, dusty birthplaces of stars and directly study the atmospheres of exoplanets for telltale chemical fingerprints, including water vapor, methane, carbon dioxide, and potentially biosignatures of life. Already, JWST's early observations have astonished astronomers, revealing weather patterns on gas giants, the chemistry of hot super-Earths, and the earliest building blocks of planetary systems. But JWST is just the beginning. Looking ahead, the Nancy Grace Roman Space Telescope, set to launch in the coming years, will bring a powerful combination of wide-field vision and specialized coronagraphs, devices designed to block out a star's glare, leaving planets to shine gently in the darkness beside them. Roman's mission will dramatically expand the number of known exoplanets, and may even provide the first direct images of worlds similar in size and orbit to Earth itself. Meanwhile, on the ground, a new generation of giant telescopes rises. The Extremely Large Telescope, ELT in Chile, with its segmented mirror stretching 39 meters across, will collect more light than any visible light telescope ever built. Its adaptive optics will sharpen starlight beyond what was once thought possible from Earth's turbulent surface. The 30-meter telescope, TMT, in Hawaii and the Giant Magellan Telescope, GMT, in Chile, will join this quest, each armed with cutting-edge instruments designed to analyze the atmospheres of exoplanets, map planetary surfaces, and even search for potential technosignatures, clues of alien technology or civilization. Space-based observatories are not standing still either. Projects like Ariel, the atmospheric remote sensing infrared exoplanet large survey from the European Space Agency, will meticulously survey thousands of exoplanet atmospheres, building a statistical foundation for our search for habitable worlds and life. Future visionaries propose mission concepts such as LUVOIR, Large UV Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, grand telescopes that could one day detect pale blue dots orbiting sun-like stars, and even read their atmospheres for the signs of oceans, clouds, and maybe more. With each telescope, our reach grows, not just in the number of planets discovered, but in the stories we can tell about those planets, their climate, their chemistry, and even their potential for hosting life. No longer will exoplanets be anonymous dots, but worlds with weather, seasons, and perhaps one day, recognized as places real enough to imagine our own presence there. This cascade of progress is powered not just by technology, but by a global collaboration. Engineers, astronomers, programmers, and dreamers scattered across continents and united by a single, persistent question: what is it like out there? The answers as they arrive will continue to surprise, humble, frighten, and inspire us. As you prepare to slip into sleep, picture these great telescopes standing sentinel under the dark sky or gliding high above the Earth, each a gentle eye open to the universe, each one bringing us closer to distant shores and the possibility of company we have only just begun to imagine. In their mirrors and detectors is written our longing for knowledge, our restlessness, and our dreamy hope to know what it is to share this vast, storied universe. As your mind drifts, consider how space exploration connects to the wonder of sleep and dreams. With the last gentle breaths of the day easing into darkness, let's let the boundaries between science and dreams blur just a touch. There is something deeply kindred between the act of drifting off to sleep and the spirit of exploring distant worlds. Both invite us to step beyond the limits of what we know, to release the constraints of the ordinary, and to voyage into landscapes colored as much by imagination as by observation. As our bodies rest, our minds remain travelers, crossing inner frontiers that, like the stars above, stretch out endlessly. When scientists scan the sky for new exoplanets or search atmospheres for the chemistry of life, they are engaging, in a sense, in a cosmic daydream. The instruments and analysis are sharp and precise, grounded in math and physics, but what carries them forward, what keeps them asking the next question, running the next experiment, is something softer, more mysterious, a restless, creative curiosity. It's the same impulse that in childhood made us look for shapes in the clouds, or conjure whole worlds before sleep closed our eyes. Space exploration and the scientific quest for other worlds is humanity's collective dreaming made real. Slow, careful, but also threaded with hope and wonder. Think of how, in the safety and stillness of night, your mind slips into dreams peopled by friends and strangers, by places both remembered and invented. Astronomers, in their own waking way, do something very similar. They peer into the vastness, following clues and patterns, often not knowing what they'll find, but trusting that the universe is filled with surprises. The kinship between outer exploration and inner wandering is more than metaphor. When you rest, your brain weaves together memories, ideas, and emotions, often arriving at insights or creative connections that daylight might never have produced. Many scientists, artists, and inventors have found inspiration in dreams or in the liminal moments just before sleep. Perhaps some of the grandest imaginings, worlds with purple seas or bioluminescent forests, civilizations with languages as gentle as music, will one day find echoes in real discoveries among the stars. The act of sleep itself, confirmation that all living things need time to recuperate, consolidate, and refresh, connects us to a grander biological truth, one that would surely apply to any life we might someday find on a distant planet. Everything alive, everywhere, must find its own rhythm, a cycle of activity and renewal, a balance between reaching out and drawing inward. So as you let yourself drift further, tucked safely on a small blue planet, remember that every time you close your eyes and let your mind roam, you are practicing in miniature the great adventure of the human species, voyaging out, coming home, and carrying a spark of curiosity that outshines even the darkness of space. Our dreams, quiet, persistent, are themselves a form of exploration. Tonight, as the stars keep their silent vigil overhead and your own journey into sleep begins, you are a participant in this endless search. May your dreams be as wondrous, as gentle, and as vast as the universe waiting just beyond your window.